Okay, so can everyone see the slides that are on the screen on right now? So just let me know in the chat if you can see this. Okay, sweet. So today we will be covering some stuff on triangles, and then to begin our tutorial, we're just gonna revisit last week's content. So last week we had this question here, and we actually didn't have time to finish it. So I'll give you guys let's say 5 minutes to work on this question, like just as a warm-up question. You don't need any special theorems, so just have a go at this question. It's really easy. Okay, I'll give you guys 5 minutes. I'll give you guys 2 more minutes. Okay, so do you guys need more time, or do you guys want me to go through the question now? More time? Okay, I'll give you guys 2 more minutes. Also, if you have any thoughts, just drop them in the chat and I'll have a look over your working stuff. So do you guys need more time? Just can someone just say something in the chat? So if I know that if you guys need more time. Okay, I'll just go through this. Okay, so what is a property of circles? So let's say if we consider this line here, then since these circles are tangent to each other, right? Because C4 is internally tangent to both C1 and C2 and externally tangent to C3. That means this line here, which is perpendicular to the tangent at this point here, would be 90 degrees, right? So let's just draw this line here. And we're trying to find the radius of C4. So for now, we can just give C4, the radius of C4, a random variable. So let's just call it R. Or actually, let's make it X. So the radius of C4 is X. So if we draw this line here, then this small segment here would be X, right? Because it's the radius of C4. Now, what else do we know? We know that from this point here to this point here, that's also 1, right? Because it's also the radius of circle C1, right? So this segment would be that. So we can form a triangle like since this is 1 and this distance is X. This distance here, I'll just use a different color. So it's a bit messy, but so the green distance here would just be simply 1 minus X, correct? Because it's the radius of circle C1, which is 1, minus the radius of C4, which is X. So it'd be 1 minus X. And then what about this distance here? Let's say we draw a line going through the middle of C4. Then this would bisect this line here, right? So the distance here, so this distance here would be 1 over 4. So let me just erase everything just to make everything more clear. So if I draw this line here, and let's say I shift this triangle over here, I relabel the lengths here. So my hypotenuse will be X, right? That's what we got earlier. And then this distance here will be 1 over 4. Now, this is a right angle triangle, right? So if we could find this length here, like represent it in terms of X or something, then we can simply use Pythagoras to find the length of X, right? Because it will equation, and then we can solve the equation to get X. So we're trying to find this distance here. So what is this distance? I'll give you guys 2 minutes to figure out how we could represent this length here in terms of X. So I'll give you guys 2 minutes. Has anyone figured out how we could represent the blue line in terms of x? So if you guys know, just drop the solution in the chat and I have a look. What do you guys need more time? I'll give you guys 2 more. Okay, so let's just consider this segment, this line here, and let's say we extend it here. Then let's call this point T. So let me just erase everything. So if we call this point T, then so let's call this point O. So what's the distance OT? Well, OT is equal to BO plus BT, correct? Because, oh wait, my bad. So label these points, so A and B. So OT is simply the distance of this plus this, right? Now, we can rewrite BT as AT minus 1/2, right? Because AT, which is this long distance, minus 1/2 gives me BT. So now I can basically just sub in my known values into someone said something. Is it 3/4? Yes. Good job. It is 3/4. And I'll show you guys why because so Josie, good job on finding that. BO is 1/4, right? Because it's half of 1/2, which is AB. AT, well, what is AT? Well, AT is just 1, right? Because it's the same radius as circle C3. So sum of these numbers and we get that OT is equal to 3/4. Now, 3/4 is the radius of C what? I think it's C3, I think. So the small circle here. So if that's the radius of Josie said something. Yeah, that's true. It will be 3/4 plus x. So let me just erase everything. Since we know that this length here, the radius of C3 is 3/4, right? Then this distance here will be 3/4, correct? So this distance here. Now we can actually get the last length of the triangle that we found earlier because we can add 3/4 to the radius of C4, which is x, right? So the length of this triangle would be 3/4 plus x. And then like before, we have these numbers for our triangle lengths. So does anyone have any questions so far? All right, no questions. So moving on from this, we can basically just use Pythagoras to form an equation. So it would be 1 minus x squared equals 1/4 plus x squared plus 1/4 squared. Correct? Because that's just Pythagoras, right? And we can just solve this equation. So just doing some algebra here, we get yeah, 1 minus 2x plus x squared equals to 9/16 plus 3/2x plus x squared plus 1/16. So these cancel, right? And then I have 7 over 2x equals 1 minus 9 minus 10. So it'll be wait, 16 minus 9, 7. So it'll be 6 over 16. 6 over 56. And that simplifies to 3 over 28. So 3 over 28 is my x. And since x is the radius of circle C4, we can say that C4 radius equals 3 over 28. So that's how you would go about solving this question. Does anyone have any questions? Yo, if you have any questions, just drop them in the chat. I'll give you guys 2 minutes to reflect on this question. Okay, if there are no questions, I'm just gonna move on to today's content. Okay, so just give me a sec. Let me just erase everything. Okay, so today we're gonna look at Menelaus's theorem. So has anyone seen this theorem before? Um, okay, so this is a very important theorem in Math Olympiad. So today we're just gonna cover it and we're gonna do some questions afterwards. So okay, so if line PQ, transversal line PQ intersects AB on triangle ABC, where P is on the line BC, Q is on the extension of AC, and R is on the intersection of PQ and AB, then the product of PB over CP, QC over QA, and AR over RB equals 1. And note that the points are all collinear, so meaning that it's a points Q, AC, they all lie on the same line. QRP lie on the same line. So I'll give you guys 2 minutes to just take in this information because we will be using this theorem in the next question. So to make it more clear for you guys, I'm just gonna color code the lengths. So PB, which is this one, CP. So if we multiply the ratio of that to that, use a different color. So QC, which is this one here, and then QA. And then lastly we have this is AR multiplied by RB. So you want to be really careful not to get the ratios wrong because especially this one here, a common mistake is that people find the ratios between QA and AC because the other lengths of the triangle follow a similar pattern, but you have to be careful with some QC over QA, so the very long one over the very short one. So does anyone have any questions regarding this theorem? Okay, so do you guys all have access to the slideshow? Because the next question will need this theorem, and it's not going to be on the screen, so you guys might have to I don't know, use the slideshow or search it up on Google when you do the question. Okay, so moving on to the question that I have for you guys. Just 1 second. Oh wait, before we do the question, can you guys try proving this theorem? So you guys from I think 2 weeks ago, or no, 2 lessons ago we did similar triangles, right? So try and prove this theorem using similar triangles because what we have here, the theorem, right? We have ratios of lengths. And when we do ratios of lengths, right, we should be thinking of similar triangles. So just have a go at proving this theorem. I'll give you guys 5 minutes and I'll go over the solution. And if you guys have a solution, please say it in the chat because I don't know, I like seeing audience participation. So 5 minutes and we'll come back to this. Okay, so I've given you guys two hints. So the first one is triangle RBP is similar to ABK. And you guys know which triangle QCP could be similar to? Okay, so Josie said ACK. So let's take a look. So QCP is this large one here, right? And then AKC. So what I've done here, right? Oh, I forgot to tell you guys, K is just a line that's parallel to QP. So we draw an auxiliary line that's parallel. So Josie's saying that QCP is similar to triangle AC oops. Um Triangle ACK. Yeah. And wait, let me think. Um yeah. So Oh wait, guys, my battery's dying. Wait, yeah, I have 5 minutes left. Okay, so what we can do here, we can find ratios between the triangles, right? So I know that since RBP is similar to ABK, I know that AR. Okay, guys, if I disconnect, just wait 5 minutes and I'll be back because my battery's kind of dead at the moment. All right, so we know that this is true, right? And then we also know that QC is 2QA is equal to CP over KP, right? Because they're similar, right? So what can we do from here? Well, we can. So let's see what quantities we have already. So we have PB here, CP. We have QC, we have QA. So the only length that we don't need, I think it's KP here. So this is like the most extra thing here. So how do we get rid of KP? Well, we can actually multiply the two equations, right? Because if we multiply the two equations together, we get right. So that's what we get when we multiply the two equations together. And what happens is that the length KP cancels, right? And now what we're left with is what we wanted, which is PB over CP multiplied by QC, the QA multiplied by over RB. So if we rearrange this, we should get this. So I'll give you guys a question. So just have a go. Um, wait, just one sec. How do Okay, so this is the question I want you guys to do. So just take 5 minutes. Oh, wait, whoops. All right, this question, and just take 5 minutes to have a go. Okay, I'll give you guys 5 more minutes, and I'm just gonna quickly leave the meeting. I'll be back in 5 minutes. So just have a go at this. Okay, I'll give you guys a hint in 2 minutes. Okay, how much more time do you guys need? I'll give you guys let's say 2 more minutes. Actually, I'm gonna give you guys a hint. So just have a look on the screen. Okay, so given this equation here, I mean this expression here, we know that BF to FC, I mean CO to CA to DA, right? Because we know that AD to DC is 1 to 2. And that means CA to DA must be 3 to 1, right? And then what's DE over BE? Well, since E is the midpoint of B and D, we know that BE must be equal to ED, right? So this ratio is equal to 1. So this really just simplifies to be 3 multiplied by BF over FC equal to 1 because we're using Menelaus's theorem. So that basically tells us BF to FC equals 1 over 3. Okay, does that make sense? Okay, so given this hint, try and figure out the area of EBF. So I'll give you guys more time. I feel like this question is a bit difficult, so maybe just take down the hints, and I really want you guys to use your own problem solving skills. So we'll do this question, we'll cover the solution next week, but I really want you guys to try this question for yourself, because just having me go over the solution isn't that useful compared to you guys working the question on your own. So we'll come back to this question next week, but please have a go using these hints, and we can move on to another question for now. So Math Olympiad is just really just using your your own self to solve these questions. The only way to get better at doing questions is doing it by yourself. So that's why I'm giving you guys more time to do the questions. So this is another question, and just have a go, and I'll drop a hint maybe 2 minutes later. Okay, so the hint I want to give you guys is we can use Mendelauss's theorem on triangle AXC. And we can make the transversal equal to B R1. So what does this give us? This tells us that AR to RX multiplied by XB over BC multiplied by CY over YA AY equals 1, right? Because we're taking this triangle here, ACX, taking AR RX multiplied by Y, wait, XB, what, hold on, right, XB, BC, right, that's our transversal, and then CY and CA. So we're just using the theorem like we would normally do. And given this information, just have a go at doing this question. You guys can still hear me, right? Like, I'll give you guys 5 more minutes. 5 more minutes. Okay. So what do we already know? We know that AY over YC is equal to P, and then AR over RX is equal to Q, right? And then can you guys see where this takes us? Because what do we have here? AY over CY. Isn't that just P? And then AR over RX. Isn't that just Q? Right? So we can express XB over BC. Oh, no. AR over RX over... Sorry, this should be 1 over P. So if we rearrange this, we should get Q over P. So does anyone have any questions so far? Right, no? Okay. So we can actually expand this. What is this one? Yeah, okay, so we can rewrite this as BC over XB equals Q over P, correct? Wait, this doesn't seem right. No, this should be P over Q, and then back here, this should be Q over P. So BC over XB equals Q over P. Now, what is BC equal to? BC is equal to CX plus XB, right? So rewrite this as BX plus XC over BX. Now, what are we actually trying to find? We're actually trying to find BX over XC, right? So what follows is that we can cancel this. We can rewrite this as 1 plus XC over BX equal to Q over P, right? And since we want to find BX over XC, we can just do some algebra. So XC over BX will be equal to Q minus P, right? Just simple algebra, moving this one over here. And I'm trying to find BX over XC. So to find BX over XC, I would just inverse this. So flip it around. So I should get Q minus P. That's my solution. Does that make sense? So I'll give you guys just 1 minute to look through my working. If you guys have any questions, please ask in the chat. Take your time. Okay, guys, if there are no questions, I'm just going to move on to the next slide. So, okay, so the next thing is this theorem. So just have a minute to read the slide and I'll come back. Okay, so what this theorem tells us is let's say we have a triangle ABC, right? And then we let D, EF be points on lines BC, CA, AB respectively. Then lines AD, BE, CF are concurrent if and only if this product holds. And note that the points have to be collinear, so AEC, AXD, and so on must be on the same line. All right, so I'm just gonna, like before, I'm gonna color code the lines for you guys. Someone asked a current question. I'll give you guys wait, just let me color code it first, then I'll come back to your question. Okay, so I'll use red. So concurrent basically just means well, AD. So lines AD, BE, and CF they intersect at one point. So that's what concurrent means. They intersect at one point and one side. How do I? Okay, so BD over DC multiplied by CE over EA multiplied by AF over FB equals 1. So this one's actually more easier to remember because there's no strange transverse line like before. So this one's really easy to remember. And when you're using this theorem, just make sure to be careful. You don't want to, accidentally write DC over BD. So it should always be BD over DC. So just be consistent with your ratios. So if you write DC over BD, then everything else must be reversed. So I'll give you guys 2 minutes to just take this in. Okay, so moving on, I want you guys to try and prove this theorem. So like before, previously we proved Minier-Loss's theorem. So just have a go at proving Puver's theorem. So I'll give you guys some time. Okay, guys. So Ethan, the other instructors, is he's gonna cover the proof. So I'm just gonna wait for him to be ready. So for now, just try and prove the theorem. Um, don't search it up on Google. Try and prove it yourself. And I'll give you guys some more time. Does anyone have any ideas as to how we can prove this theorem? If you have any thoughts or maybe questions, you can drop them in the chat. This one's a bit more tricky, so um, I don't expect you guys to find the solution in one go. So just take some time, look for some relationships and get the solution. Yep.
All right, so I'll be taking over from now. So, does anyone have like any ideas on how to prove this theorem, or are we? Should I give like a bit of a hint, I guess, for everyone? Because I think this proof, um, it uses ideas I think everyone knows, but it's like there's just they've just never been like used in this way, I guess, if you kind of get what I mean. Does anyone have like any sort of ideas? I'll just give a hint now, I guess. So let's just focus on like each term at a time. So let's just focus on like one of these fractions for now. So let's focus on like BD over DC for now and ignore everything else. Um, so the way we're gonna approach this problem is we're gonna approach it using the areas of triangles. So for example, if I were to take this triangle here, BCX, and then we're going to consider how it's made up of two triangles, so BXD and XDC. So if we draw the height of both these triangles, you'll notice that they have the exact same height, right? They both have a height of, let's say, H. So then we know that the area, like this is the notation for area of a triangle, these square brackets. So we know that the area of BXD of triangle BXD equals half H times BD, right? And we also know that the area of triangle CXD equals half H times CD. So then if we were to divide both of these equations by each other, we would get the area of BXD over the area of CXD is equal to half H times BD over half H times CD. And like these cancel out, so you get BD over CD, right? And similarly, you can do the same thing for like this big triangle here, ABD and ACD. So then if you were just repeat the same process, you'll get that BD over CD equals the area of AB, okay, ABD over the area of ACD. Does everyone follow so far? Did I go a bit too fast? Is everyone all good? I'll leave you guys to, I guess, continue from here. I guess I'll add another useful property that you have to use in this question. I'm not sure if any of you have come across this before, but it's a nice algebraic property. So let's say we have two fractions that are equal to each other. So let's say a plus a over b equals c over d. Then that also tells us that both of these fractions are equal to the sum of the numerators and the sum of the denominators, like over each other as a fraction. Uh, you can try prove this yourself algebraically, but this is a very, like, I guess, useful algebraic property that is used in this question. So try use this in combination with like these two ratios that we've gotten of like we have of each other, because we know that BD over CD equals the area of triangle BXD over the area of triangle CXD equals the area of triangle ABD over the area of triangle ACD, right? And try use like this property on like this, like try treat it as like algebra, I guess. Do try prove the algebraic relation first. Don't just like use it without knowing the proof. All right, I'm gonna keep going with the solution. So, I guess the key observation you have to make at this step is that the area of ABD, like the area of triangle ABD, is actually equal to the area of triangle EXD plus the area of triangle ABX, right? You can see visually from the diagram, like this big triangle here is equal to the sum of like this triangle plus this triangle. So then we can rearrange, or we can kind of change this ratio. Well, I should just go here. So then we have BXD plus ABX over, and then the bottom ace triangle ACD is also equal to triangle CXD, or the area of triangle CXD plus the area of triangle ACX. And then you notice that, this term is the same as this term, and this term is the same as this term. So then we can use our relationship over here on the left hand side to show that BD over CD is also equal to the area of ABX over the area of ACX. Does everyone understand that so far? Because like if you let, for example, the area of BXD equal A and the area of CXD equal B, and then the area of ABX equals C and the area of ACX equal D, then we have A over B equals A plus C over B plus D, which implies that that's also equal to C over D. Um, so now we've shown that the area of ABX over the area of ACX is equal to BD over CD. And then you can use this basically the exact same method to show that CE over EA is equal to the area ABX. ABX is on the bottom. The area of BCX over the area of ABX. And then AF over BF equals the triangle area of triangle ACX over the area of triangle BCX. So then when you multiply it all out, you get, so this thing multiplied out is the same as ABX. Okay, I'm just going to ignore the square brackets because it's very tiring to draw out, but it's the same as this basically over ABX times ACX over BCX. And then everything cancels. So this cancels with this cancels with this, and this cancels with this. So in the when you take the product of the three ratios, you get one. So that's the basic outline of the proof. I would recommend, if you haven't already done so, to re-go through the steps with like each of these ratios. So go through all the steps for CE over EA, the exact same steps I did for BD over DC, and then do it again with AF over FB, just so you like understand all the steps, I guess. So does everyone understand the proof, or should I, does anyone want me to like go over the proof a bit slower? No. What's the time? 7:50. Does anyone want to continue with the lesson, or should we just stop it here and then continue on next lesson? We should probably stop it here because we can't really do anything in 10 minutes. Um, I guess for homework, if you really want to do homework, just go over this proof of Chavis theorem again if you didn't understand it. So, yeah, that's I guess the lesson's over then. Does anyone if you have no more questions, feel free to leave then, I guess. Thank you very much. Does anyone have any questions? If you don't, you are free to leave. Am I allowed to leave as well?